Hello everyone. Today we will discuss about the new concept, which is electric flux. So before we discuss this technically, we need to understand what is the meaning of flux. Flux means flow. Here we are discussing about electric flux, that means we will discuss about electric flow. But we need to understand the concept of electric flux using water flow, because electric flux is not visible. So we can understand this by taking a concept where you can visualize something, right? So we'll take the water flow through a pipe and consider a wire ring, right, placed normal to that water flow. Now if the water flow is flowing like this, if we place this ring normally to the water flow, what will happen? All the maximum water will pass through this ring, right? And if we place this ring like this, water flow is in the same direction, there will be no flow of water through this ring. And if we place the ring like this, the water flow will be there, but this will be less as compared to the position when it is held perpendicular to the water flow. So that means water flux is maximum, or you can say water flow is maximum when the ring is held perpendicular to the water flow. Perpendicular means here the plane of the ring is perpendicular to the water flow. Here the plane of the ring is parallel to the water flow, so no water is passing through it. When the ring is kept in some direction which is other than the perpendicular and the parallel, in this case there will be water flow, but it will be less. So we can understand the electric flux by comparing it with this case. So when we define electric flux, we define electric flux as the number of electric field lines passing through an area normally, right? So that means whatever be the area, if it is placed normally, there will be maximum flow of electric field lines, and if it is the plane of the area is parallel to the electric field, then there will be no flow of electric field lines through that area. If it is in some other direction, then there will be less flow of electric field lines. And how much, that we will understand using the diagrams over here. So what is electric flux? It is the number of electric field lines passing normally through an area placed in electric field, right? We know that in case the electric field is uniform, then we draw parallel electric field lines. So I am just drawing a diagram here. I will discuss all the three cases. So first case I am drawing when the area is placed normal to the electric field. So this is the area and this is the direction of electric field, right? In this case, I am drawing the case when the area, surface of the area is parallel to the electric field. This is the direction of electric field in all the cases. So this is the direction of electric field. And in this case, I am drawing the area, the plane of this area is in some direction with the electric field. Now here we need to understand the concept of areal vector. Normally we say that what will be the direction of area, but technically area has some direction, and that I will tell you how do we consider the direction of the area. Suppose if I have this area, right, then this way, there will be no specific direction. So the area vector is considered as a direction which is normally outward from the surface area, right. So that means this direction will point along the areal vector for this surface. Are you getting? So this means if I am drawing this plane perpendicular to the electric field, the direction of this areal vector will be along the electric field, right. So the direction of areal vector in first case will be this way, right. So if I mark that this is a small area ds which I am considering here, then this will be the direction of the areal vector ds vector, right. In this case, the areal vector will be normally outward to this area. So if S is the total area and ds is the small area which I am considering over here, then ds vector has this direction, right. And we can also show the direction by unit vector. So we can mention that this is ds cap or n cap also we can show. In this case, the direction which is normally outward will be this way, right. So if I am considering this ds area here, then ds vector will be normally outward to this surface area. This is the plane, so this will be the normally outward. So this will not be along electric field, this will be at some angle which I am showing over here. So this is the direction of electric field. So what is the angle between the electric field and the ds vector? Theta is the angle between the electric field and the ds vector. Now in this case, this is arbitrary case, we can consider the flux for any orientation, any angle of the surface area. So we know that electric flux, that is the electric field lines, number of electric field lines passing normally through an area placed perpendicular to it. That means in this case the number of field lines will be maximum, in this case 0, in this case some part will be there, and this field lines is proportional to the product of E and the surface area. So I can write it like this also, E ds cos theta. Why so? Because if I am having this ds vector, right, and this is the direction which we know that the direction of electric field is also the same, but here what I want to find is, I want to find the component of this surface area along this direction. So this will be ds cos theta and this will be ds sin theta. Now again compare the case. In this case, the normal vector is this. The normally outward vector, that is the direction of aerial vector, is this, which is perpendicular to the electric field. So when the area is kept like this, when the aerial vector is perpendicular to electric field, no electric field lines are passing. When the surface area vector is along the electric field, then maximum field lines are passing. So if we take this arbitrary case, the case where the aerial vector is perpendicular to the electric field, there will be no flow of electric field lines. Now here I can mention this electric field direction just to remind you that this component of surface area is perpendicular to electric field. So when surface area vector is perpendicular to electric field, then no field lines pass. So that means no field lines pass through the ds sin theta component of aerial vector. So here for your reminder I am mentioning as in figure 2. So I am marking this as figure 1, this as figure 2 and this as figure 3. So I am marking similar to figure 2 where aerial vector is perpendicular to electric field, right? So in this case, through this surface area vector, the electric field lines will not pass, but the case where the electric field is parallel to the surface area vector, like this case, electric field is parallel to the surface area vector, the field lines will pass. So for the arbitrary case, general case, the electric field lines will pass through only this component of the area. So I am just mentioning this also. Field lines will pass through the aerial vector ds cos theta component only, right? So here we can compare again similar to figure 1. Where aerial vector is parallel to the electric field. Right? So this what we are doing here is discussion of case third, that is general case, right? So this is an important point. So from here we know that flux lines are proportional to the product of the electric field and the surface area vector component, right? So we can write this in vector form like this. So if we are talking about ds area, then we will mention that this is d phi. So if I am marking this in vector form, so d phi is E dot ds vector. This is the flux. This is electric flux. So in some books you will find simply phi, not d phi. So if I am finding this from ds surface area, then the flux will be d phi is equal to E dot ds, or if I am finding the total flux, this will be E dot surface area vector. What is this? This is dot product or scalar product. Just recall the concept of 11th. When we have a dot product means if the product of two vector quantities is a scalar quantity, then it is called dot product or scalar product. So in this case, electric field is also a vector, surface area is also considered vector. So the product of these two is a scalar quantity, that is flux. So that's why this can be represented as E dot S vector, because we know that A vector dot B vector is equal to C vector and this can be written as AB cos of theta. So the formula, if we are writing small electric flux, then we can write d phi is equal to E dot ds when we are finding the flux through ds surface area. And if we are finding it from the complete surface area, then we can mention phi is equal to E dot s. So we can specify here that phi, that is electric flux, is a scalar quantity. Its SI unit is unit of electric field multiplied by unit of surface area. So unit of electric field is Newton per Coulomb and surface area is meter square. So Newton meter square per Coulomb is the SI unit of electric flux. So this was all about the concept of electric flux. Hope you understood the concept. That's all for now. Have a nice day.